Hello, everyone. Welcome to our first IB Physics SL Year 1 live lesson. This is Mr. Keppel, and I'm joined here today by several students. If you want to introduce yourself, please say hello now.
Hi.
Who is this?
Oh, it's Pharaoh.
Oh, Farrell's here. Who else is joining us today on voice chat? No one else on voice? Laura was here a minute ago, so is Aaron. If they come on, we'll make sure to say hello to them. All right, so the first thing we're going to do is get out this handout that I gave you guys in the before times, before our society shut down. It's just the continuation of this thermal physics page. You guys remember we talked about like states of matter and things like that. You know what I'm going to do is while you're getting out that page, I'm just going to show you the work that we had already completed on this. So we had talked about the different phases of matter. There are solid, liquid, and gases. We had discussed the interparticle forces that connect those particles together. So when you're in a solid, remember we talked about how you have two atoms. If you squeeze two atoms together, they repel each other, and if they're brought apart, they attract each other together again. So we talked about these interparticle forces and how it somewhat relates to what state of matter you're in. So if you're in a solid, they're close together, the particles are stuck together. If you're in a gas, they're kind of moving around a little bit, and if you're in, I'm sorry, in a liquid, they're kind of moving around, but they're still stuck. And then in a gas, they're completely free from each other and flying all over the place, where there's no interparticle forces. And so this is what we had written down on our pages. Hopefully, you guys remember this. I know it was a long time ago. Let's see, we also talked about what is temperature. So temperature, this is the actual answer, but I don't think I expected you guys to actually know what it was yet. So just that temperature is a macroscopic property of a microscopic system of particles. It's measured with a thermometer and it indicates how hot or cold a substance is. More specifically, temperature relates to the motion of the particles in the sample. Temperature measures the average kinetic energy of the particles. So I just talking about this, why am I like doing that? I want like a different here. Macroscopic properties. So like the idea is that if you have an object, which really consists of a lots of different particles moving around and jiggling all over the place, the macroscopic property that you detect is the temperature. Like if you touch it and you feel it and it feels hot, that's a macroscopic property, like a human-sized property. But really, it's a result of microscopic motions of those particles and the microscopic energy that those particles have as they move around. So if the particles move around more quickly with more energy, you're going to feel that as a hotter temperature. Ooh, someone else just joined. I thought I heard a sound. Who's
Yeah,
that?
I think it's Aaron.
Aaron, is your mic working yet? Just feel free to jump in whenever if you want to test if the mic works. This is really casual. Don't worry about messing up the video or anything. Okay, the next thing we talked about was the Boltzmann's equation. So we said this was the equation that shows you based on the temperature of an object, you can find the average kinetic energy of the particles in that object, and you just have this Boltzmann's constant here. What did we do next? Oh, we looked at what the units of temperature are. There are the units called Kelvin. That's the SI unit. What else did we talk about? Oh yeah, we talked about how when you use this equation, you always have to plug in the temperature in Kelvin. You cannot plug it in Celsius. You'll get the wrong answer. And so remember, we solved this. We found what's the average kinetic energy of the molecules in an ice cube when the temperature is zero, and we found this answer. I'm gonna check in on a Discord real quick and see who joined us. So we got Aaron, we got Faro, we got Laura, we got Roberto. Roberto, are you here? Can you hear us? Hey, I could kind of hear you. I'll go back to here. So we're getting out this page. So I believe when we left, I mean, I don't remember. It was so long ago, and like so much has happened since then. Uh, what does it say? Oh yeah. So we talked about how what if you had a sample of particles and you started to suck away energy from them? Like you have these particles jigging away, and you started removing energy from those particles. What would eventually happen if you just kept taking away more and more energy? The particles would start to. You guys can jump in here. If you take away energy from the particles, they would start to do what?
They will start to become static.
Yeah, they would slow down, they would stop. And at that point, the energy of that system would be zero. There'd be no more energy left. And that temperature, we call that 0 Kelvin. It's called absolute zero. And so that's what we kind of talked about here. At that point, the pressure is zero and all the particle motion is stopped. All right. So what questions do you guys have for me about anything that we've talked about here? I'll pull up the chat. If you guys want to chat in here, you can chat in here if you have questions. So you can either chat in voice chat or you can chat in this physics chat channel right here. I'll just pause for questions. We're good. Ready to
Yeah, I
start?
think
You
we're
got the
good.
paper out?
I'm looking for it.
Okay. You're probably like, why would I need papers from a million years ago? Feels like it was a million years ago. I hope you guys have been healthy and that your families are well, and I hope you don't have anybody sick. I'm really worried about you guys.
Nah, everything's fine. I still don't believe in the virus because I've never seen anyone with it. I'm just kidding.
You should believe in it. I've you know, this is unprecedented. I don't remember the last time that we've ever shut down schools for this amount of time. It's pretty crazy.
Hmm.
Yeah, it's really scary too. Just how this virus just attacks people's lungs. Like the doctors are saying they've never seen anything like it. It's really scary. All right. Well, if we can't find the papers now, that's fine. You can just do it later when you're watching the video. So I want to talk to you guys about thermometers, how they work, and just about like your regular liquid in a glass thermometer. So we'll just read this. So temperature can be measured with a thermometer, which is simply a device that has one property that changes in a predictable way as temperature changes. For a liquid in a glass thermometer, that property is the volume. So the volume of this liquid in the glass, the volume will change predictably as we heat something up or cool it down. It, the cross-sectional area is going to stay the same. Like the area across this tube is going to be the same in both cases, but you can see that the volume, the height of the liquid has changed. So we can use this to measure temperature. The first thing though is we have to calibrate it. So calibrating it means you need to choose two locations and name those temperatures. So what we do for the Celsius scale is we pick this point, which is the temperature where ice melts, and we call that, does anyone know what we call that in the Celsius scale?
0.
It is 0 degrees Celsius. And then we call this point where water boils, we call that
100.
100. And so now that you've got these 2 points established, you can create a scale. And so if something's like halfway between, then we know like right there, that would be about 50 degrees Celsius. So you have to choose those 2 points first and predefine those 2 points, and then you can create a scale from that. What other temperature scales have you guys heard of? Open up the chat again.
Fahrenheit,
Fahrenheit,
Kelvin.
Kelvin, Celsius. So all these different scales use two different points to determine their temperature scale. So the Celsius scale uses boiling and freezing for water, and the Kelvin scale uses absolute zero and the triple point of water. The triple point is the temperature where the water can exist as a liquid, gas, and a solid all at the same time. And the Fahrenheit scale uses a mysterious mechanism that we aren't really sure of where it came from, but the story goes something like Gabriel Fahrenheit went out on the coldest day of the year in Germany and he called that 0 Fahrenheit. And then he stuck his thermometer. He was the inventor of the thermometer. And he stuck the thermometer under his armpit and said that was 100 degrees Fahrenheit. So he based the temperature scale off us, off of humans. But the point is, anytime you want to create a temperature scale, you have to have two temperatures that you've based your scale off of. All right, so we calibrated this thermometer by labeling these two temperatures points and we've created a scale here. Okay, so we say when a thermometer comes into contact, I'm going to move my webcam over here. When a thermometer comes into contact with a body, a thermal interaction takes place and energy is transferred until the thermometer and the body are at the same temperature. This is called thermal equilibrium. So if you take like a material and you stick your temperature and you stick your thermometer in it, what's going to happen is energy is going to flow between the two objects until they have the same temperature. And then that's how thermometers work is they become the same temperature as the body that you're measuring. The reading on the thermometer is therefore the temperature of the body. All right. Oh, I'm showing you guys the answers. I'm supposed to go back to the blank page. Little glitch there. All right. So what I want to do first is outline three physical limitations of using a liquid and a gas thermometer to measure temperature. So the first limitation is really going to come from that idea where like we've stuck this object into another object. So are we actually measuring the temperature of this body?
No,
No, we're measuring the
it's the
temperature
temperature.
of the
The two things
thermometer.
combined.
Right. And so that's your first limitation of using a liquid and a gas. I have my answers here. I'm going to make sure I don't mess this up. So the issue is like the thermometer isn't going to perfectly hold in all that energy that it absorbed from the body. The thermometer is going to be constantly radiating some of that energy. It's like some energy is going to be constantly coming out of the thermometer. And what's that going to do to the temperature of the thermometer if it's constantly radiating energy out from it?
It loses energy.
That would make it lose energy. And so that's the first limitation of a liquid and glass thermometer is that the thermometer is not insulated, and so it can, heat can be. Well, I don't think I've told you guys what heat is yet, but heat is a transfer of this microscopic energy that these particles have. So the first limitation is that the thermometer is not insulated. So thermometer is not insulated. I can't remember how to spell insulated. Oh, there you go. Insulated. And so what this means is that energy can escape. I'm having to keep my surface at this weird angle so that the webcam is on my face, and it makes it like really hard to write on it. I tried to purchase a new webcam that I could hook up on a tripod, so I didn't have to worry about the angle of my surface. But every single site that had the webcams are either like twice as expensive as they normally are, or they're on back order until May. So I have to use my built-in
Dang.
camera. I guess all the teachers across America are trying to buy webcams right now. All right, so that's number one, limitation number one. Limitation number two is that not all liquid and glass thermometers will be the same. So not all liquid and glass thermometers will be the same. So this is kind of a weird one, but like if you think about it, if you're manufacturing this thermometer, like you forge this glass together, like no two tubes of glass will be the same at a microscopic level. They'll all be slightly different. Like maybe like if you were to zoom in really good on that thermometer, like maybe one will be like relatively smooth, whereas like another one, maybe there's like imperfections and it's kind of like jaggedy. And so you could say like no two thermometers are ever going to be the same. And so this could lead you to the point where like you stick one thermometer in an object and then you stick another thermometer in the object and they read two different things. Like that's entirely possible with liquid and glass thermometers. So it's a major limitation of using a liquid and glass thermometer. And the third limitation is that every thermometer will agree on those 2 points. So no matter what thermometer you have, they'll all agree on the 0 and they'll all agree on the 100 because that's how you built the thermometer. You establish those 2 points as being reference points. Like those are for sure the temperature at those points. But they won't necessarily agree on in between points. Like one thermometer might say that's 50, whereas another one might say it's 51. So no two thermometers are the same. As a result, they'll agree at 0 and 100, but they won't necessarily agree at the points in between. So I'm changing my angle and it's messing up the camera. Okay. So number 3 is all thermometers. I'm like Miss Bergman here. Oh my gosh. Did you guys watch Miss Bergman's video? Jeez.
I've seen how it is all squiggly.
Michaela shared that with me this morning. I was laughing and I'm like, oh God, I'm going to do the same thing. All thermometers agree on 0 and 100, but not the points in between. So the idea is just right. You got to find a property that varies predictably with temperature. liquid and glass thermometers were the very first thermometers that we invented as humans, but they're not the best. They're a much better thermometer to use is actually an infrared thermometer where you look at the light that the object is radiating. It's called radiation. And based on the frequency of that light that it's radiating, you can tell the exact temperature of that object. Those are called infrared thermometers. Those are really good ones to use. Like I have a thermometer that you could stick it in your ear, and it like measures the infrared radiation coming off of like some blood vessels that are in your ear, and it measures that as your body temperature. Those thermometers are really good. Like there's not as much error when you're dealing with like directly measuring the light that the object is giving off. There's other types of thermometers like the digital ones, like you stick them under your tongue and they like beep and they like show you the digital readout of the temperature. Those use a device called a thermistor, which is a thermal resistor. And so we'll talk more about this when we study electricity in the fall. But the resistance of a little piece, like a little chip, the resistance of the material will change as temperature changes. And so that will, as the resistance increases, it'll decrease your current. And so you can know exactly what the temperature is. When you read the current running through this resistor, you can determine what the temperature is. That's called a thermistor. So anyway, there's lots of ways you can make thermometers, but the main idea is that you need something that changes predictably and that you always choose 2 points to create your scale. Okay, did you guys have any questions about thermometers before we move on? No one's typing in my chat. You guys need to type something in here. Type something here so I know you see it.
Uh,
Laura's typing. Yay! We're not alone, Farrell. Okay, good. It helps me knowing that there's other people there because otherwise I'm just like this old man in a dark basement, like talking to myself. So I appreciate you guys chiming in there. But are we good on thermometers?
yeah.
Okay, back to here. Okay, I'm gonna put my camera up here. All right, the picture shows a beaker of water being heated on top of a hot plate. The temperature of the water is 20 degrees Celsius, and the hot plate is 300 degrees Celsius. No wonder you call it a hot plate. As mentioned previously, two bodies that are in thermal contact, so they're touching each other, and have different temperatures will have a thermal interaction. So I want you guys to think, will energy be transferred from the water to the hot plate, or will energy be transferred from the hot plate into the water? So I want you guys to think about which direction you think that's going to be. So on your paper, check which one you think it is, and then we'll talk about it in a moment. So what we want to think about are the particles in the water. So if I draw a picture of those particles, so the water is 20 degrees Celsius. So if we think about the molecules in the water, I'm going to like zoom in on the particles. What are the particles in the water doing? Well, they're moving around pretty slowly. They're kind of randomly just moving around. But if we zoom in on the particles in the hot plate, what are those particles doing?
Moving really fast.
Yeah, that's 300 Celsius. So these things are just like shoom, shoom, like they're flying all over the place, like super, super fast. So what's going to happen when one of these slow water particles smacks into the fast hot particle? What's going to happen to the fast particle and what's going to happen to the slow particle?
Well, the fast particle is going to slow down, but the slow one is going to speed up.
Exactly. So if a fast particle slows down, what happens to its energy?
Loses energy.
Right. So the
Oh,
energy
yeah,
here is going to drop, whereas the energy up here
go up.
is going to go up. So the fast particle is going to smack into the slow particle and transfer energy from the fast particles to the cold particles. So which one of these would be the correct, which of these over here would be the correct direction that the energy flows?
The hot plate to the water.
It's going to flow from the hot plate to the water. So this is really confusing to early physicists. Like they used to think that it was like that cold. They called it frigoric. That like cold. What substances had was they had this like coldness, and the coldness would pass from one thing to another. And that's just insane. Like what we know now is actually that temperature is just a result of particles moving around. And so if you stick two objects together, and the particles are moving at different speeds in those two objects, then those particles are going bum, 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 they're going to crash into each other, and then it's going to end up changing the speeds of those particles, which is resulting in an energy transfer from one object to the other. In this case, the energy is going to go from the hot plate into the water. All right, so we just need to like justify our answer there. So basically, it's everything that I just said. So I'm gonna give you guys a minute to just like write down what you thought, like just to summarize what we just talked about there. This is the boring part where people turn off the video. All right, I'm gonna pull up my answer for you guys. So I approached it from a slightly different perspective. So what I was thinking was, we know for sure that the water is gonna get hotter. Like when you stick the water on a boiling plate, like the water, I'm sorry, when you stick the water on a hot plate, it's gonna make the water boil. And so that tells you that the water is gaining energy. So the only way for that energy to be gained by the water is if it's being lost by the hot plate. So I said, in this situation, we know that the temperature of the water will increase. From the definition of temperature, an increase in the temperature of the water means that the water particles are gaining kinetic energy. So that's coming back from this equation over here. So we know that if we're gaining temperature, that we have to be gaining kinetic energy. So if the water is heating up, it has to be, those particles have to be gaining energy. So the only possible explanation of this gain in energy is if energy is transferred to the water from the hot plate. What I like about thermal physics is every question is really simple like this. If you just think about your own experience with heating things up on a stove and stuff like that, it's all in agreement with that. Okay, so what we want to do now is we want to construct a general rule for the direction of heat flow. So what's a general rule that we could say? If you put two objects together and one object is hot and the other object is cold, what's a general rule that we can say for the direction that energy will transfer?
Energy transfer from uh, hot to cold.
Exactly right. So that's our general expression. We say that energy, or we can call it heat, energy transfers from hot objects to colder objects. That's the way it normally goes. You can make it go backwards, but it's going to be in very specific situations where you're forcing it to go backwards. Like, for example, in an air conditioner or a refrigerator, you can force this natural mechanism to go backwards. But if you just take two objects where one is hot and one is cold and you stick them together, it's always going to go naturally from hot to cold. So we just want to write that down in the last part there. So hot to cold. I want you guys to write it in a sentence. I'm just being lazy. All right, so this brings us to our first major misconception with thermal physics, and it's with the word heat. The word heat is annoying because the way we use that word in English is not the way we use it in physics. That's why I've been up to this point avoiding trying to use the word heat, because it doesn't it doesn't mean what we think it means in physics. So I'm going to give you guys the definition here of heat. In physics, heat does not mean hot. Like normally that's what you think, like in everyday life. Like, oh, turn on the heat. It's cold, turn on the heat. That's not what heat means in physics. In physics, we say that heat is a form of energy transfer. It's just like work. You guys might remember that equation we talked about in the energy topic like long ago. We said that the way you can change the energy of the system is there's two ways. You can do work on the system or you can supply heat to the system. When we say heat in physics, we're simply talking about a form of energy transfer. It's a way of getting energy from one object into another object. So specifically, we say this, that heat is energy that is transferred from one object to another as a result of a temperature difference. So two objects have to be in a thermal interaction with each other, and they have to have different temperatures, and then heat will flow. So if you take two objects that are the same temperature and you put them together, you won't have any heat flow. There has to be a hotter object and a colder object, and then heat can flow between them. Okay, so now I want to just take this back to the phases of matter and just kind of connect it all together and like put a bow on it. I think I got like 5 minutes left. We have shown that energy can transfer between objects due to a temperature difference. But where does this energy come from and where does it go? To answer this, we must consider the structure of matter. The picture below shows the motion of the particles in a solid, liquid, and a gas. So we're familiar with these pictures already. So the particles are in constant motion. How does this relate to energy? So how does the motion of the particles, how does that relate to energy? So what type of energy are we talking about if something is like moving around? What type of energy is that?
Kinetic energy.
That's kinetic energy. So the faster the particles move, the more kinetic energy they have. So this is usually referred to as thermal energy. So I'm going to write this down. So the particles, the faster the particles move, the more Ke, so it's kinetic energy. I just had a Bergman moment. The faster particles move, comma, the more kinetic energy they have. This is usually called thermal energy. So thermal energy is referring specifically to the energy of the motion of the particles in the substance. So when you look at these three pictures, in which state of matter would a substance have the most thermal energy?
The gas.
The gas, because it's moving the fastest. So you can see the particles are just zooming around over there in the gas and they're going slower in a solid. But that doesn't necessarily mean that if something is a gas, it's going to have more kinetic energy than something that's a solid. It depends on the material. The material is really going to make a difference there, like how big the particles are, or like if there's like a smaller like molecular structure within it, like water, where you've got like, you know, three atoms bonded together, or is it just like a single like monatomic? The molecular, like the substance, is going to actually matter. But just know that if it's the same substance and it's a gas, it'll always have more kinetic energy than when it's a solid. I should say molecular kinetic energy. Okay, next one. The particles exert forces on each other, right? So like remember when you have two atoms and you squeeze them, when you squeeze them together, they repel, and when they are far apart, they attract. So these particles are always exerting force on each other. So how does that relate to energy? You notice I got a lot of space here. So the motion of the particles is telling you the kinetic energy, but what does like the spacing of the particles tell you? That tells you do you guys remember?
Uh,
So motion is kinetic energy. Forces is a different type of energy. So the classic example is to think about like gravity. So if you have a ground right there and I have an object up here and it's separated from the ground,
Oh,
then
potential energy?
you got it. Then there's going to be this force of gravity pulling it down. We call that potential energy. So forces between objects when they're separated from each other, that's potential energy. So the attractive forces give rise to what we call interparticle potential energy. I'm just going to write that here. That's an E. Oh, jeez. Let's try this one more time. Interparticle potential energy. So we usually use the analogy that the particles are bonded by springs. So imagine, this is obviously not, whoa. Imagine the particles are like stuck to each other like by springs. So you imagine, I just took my keyboard off. Imagine the particles are bound by springs. Get out of here. So you imagine you got one particle here, then there's like a spring connecting it over here to this other particle. If you stretch them out, so what would happen if I pulled these particles apart from each other? So if the particles are like repelling each other, then what would happen to that spring? Whoops. It would get more stretched out. And so what would that mean about the potential energy?
That increases.
Yeah, that you have way more potential energy over here because there's a larger distance between them. If you guys remember that equation, it was 1/2 kx squared, where x is that extension length. And so since the x went up, then we have a greater amount of potential energy in them. So when you look at the phases of matter up there, which phase of matter has the most potential energy?
Gas.
Yeah, you'd say it's the gas. The way we define it though is a little bit weird. So we actually say that when it's a gas, it's zero potential energy. So if this is the potential energy, and then this is how far apart the particles are, I'll just call it x for now. Then what actually happens? I did this in the wrong place. It actually looks like this. So if my separation is there, then we actually say the potential energy looks like this. And then when it's a gas, it's up here at zero potential energy, and when it's a solid, it's down here in the negative potential energy. Since the potential energy is negative because like they're being stuck together, so you have to actually like rip them apart and free them from each other, and then it'll become a gas. And so we actually define the potential energy as being zero. And it's kind of weird. You'd say like, well, how could gas have the most potential energy when it has zero potential energy? Well, because solid has a negative potential energy. But you guys don't need to worry about all the like nitty gritty details there. All right, so this leads me to the thing I'm going to end on, and then I'm probably going to make you guys answer this question just as like a learning reflection on Google Classroom after we're done here. But basically, if we want to describe the total energy that's inside all these particles, we can't just talk about the thermal energy. We can't just talk about how fast they're moving. You also have to talk about how far apart they're spread out from each other. We also have to talk about that spacing. So to do that, we create a new word called internal energy. And so we said that internal energy is the total random kinetic energy of the particles plus the total internal interparticle potential energy. Oh my gosh, it's a mouthful. But the idea is that if you take the kinetic energy, the amount of motion the particles are experiencing, and how far apart they're spaced out, if you add those together, that's internal energy. So it's important to remember that energy doesn't just show up by making the particles move faster. It can also show up by pulling the particles apart and transitioning to different phases. All right, that's it for the first lesson, guys. I'm done. Any questions?
Okay. Nope.
So we're good. Just gonna check in the chat. What questions do you have for me? I'm gonna stop the video here. So I'm gonna post this all up onto Google Classroom, and then there'll be a little reflection assignment thing that I want you guys to fill out, and then and I'll see you guys on when's the next day? Thursday morning, Thursday 11 a.m.
Yeah.
All right. I'm gonna stop the video, but I'm not gonna stop the voice chat. The video is over.